All right. Perfect.
We're live. Look at that.
We're live. Welcome, everyone. Welcome to the session. And I would like to start with just making you kind of go back to the code you've ever written and think a little bit about how much you have thought about memory. And when you put things into data structures, how much you think about on the impact of the whole thing. And here we're not really talking about just like, well, tiny little array or tiny little set or something. We're talking about also larger sets. So, you know, whatever is a few bytes difference, if you multiply it by whatever, by big numbers, it becomes quite a bit, right? So with that, I think it's time to say a few introduction words. And since I'm the first one up here, so I'll start. My name is Rustam. I work as a chief engineer back in Oslo, Norway. And I've been Java champion since 2017. Google Developer Expert for Cloud, so GD for Cloud as well. I kind of refuse to remove Java 1 Rockstar. Had that for a while. And I also run quite a few communities in Oslo as well. So over to you.
Okay, thank you. And yeah, welcome everybody. Thank you for joining us today. So my name is Donald Robb. I'm a managing director and distinguished engineer at the Bank of New York Mellon. Our marketing name is called BNY Mellon, so I spell it out for folks that don't know that it's a bank. I am the creator of Eclipse Collections, also currently project lead and committer. For those that know the library, I have stickers with me today. If you're interested, they're up here on the table. Also Java champion. I was a member of the JSR 335 expert group, which got lambdas and streams thankfully into Java 8. So hopefully I'll enjoy using lambdas and streams like I do for the past 9 years. So I was a contributing author to 97 things every Java programmer should know as well. So.
All right.
And with that, so we will get started. So I'm going to take a flashback to a point in time in my career. I don't know if this is going to give away my age, but I've been doing this for a while. So let's talk about the problems with in-memory Java architectures back in 2004. So to give you some context, I worked in financial services, worked in a large bank, and worked in a space where we were caching everything into RAM. Unfortunately, we were in the 32-bit space, so if I recall correctly, in 32-bit, like on Windows, you can maybe get like 1.4 gigs, but we used Solaris boxes, so we had this switch that we could turn on, and we could actually get up to 4 gigs of RAM. Problem was I took over a project that was trying to cache everything and actually run calculations that would create object graphs in memory, and at the end, it was like trying to fit 6 gigs of stuff into a 4 gig space, right? It wasn't going to work. So digging into the problem a bit, we discovered that because of the object graphs that were being created, they were bidirectional, and pretty much like every parent knew its children, every child knew its parents. So in these calculated graphs, we were creating millions of small lists, sets, and maps, right? So solution at the time that we came up with was like, hey, we can roll our own Java collections that basically get rid of backing arrays and collections, so we can have a singleton set or list, not have a backing array. But it was interesting because and I wrote a blog about this. We'll talk a little bit about it later, but I felt like, who's seen The Martian? Yeah, a few people. Yeah. So I felt like Mark Watney, right? So in the face of overwhelming odds, I'm left with only one option. I'm going to have to science the shit out of this, right? So it's like, it's again, trying to jam that 6 gigs into 4 gigs. How are we going to make it work? So if we fast forward after 2004, so it was interesting. We went from 32-bit JVMs to 64-bit JVMs, and all of a sudden, like, a problem changed from being an accessible memory problem, like how much memory can we access. Now it was a question of like, how big is the hardware you can get, right? And we dealt with larger and larger caches. What's interesting is we got like a 64-bit in JDK 1.4, and when you went to 64-bit, all of a sudden, like, your heap sizes jumped because your references for objects went from 4 bytes to 8 bytes, right? And in the initial days, we didn't have this wonderful option of compressed oops, right? But that came along eventually, right? So compressed oops gave us, this nice I call it a sweet spot. You can consider a threshold like below 32 gigs. You get this niceness of having, the 32-bit, references, so 4 bytes a piece. There is something, and we used to have caches up to like 60 gigs, and beyond that, you're into pure, 64 bits. So you're going to get the extra cost for every reference, but. In order to keep our memory sizes down, because we were creating all these large caches, we wound up rolling our own memory-efficient mutable sets, maps, and lists. And a lot of those are now part of Eclipse collections. We also built primitive collections. So we've got primitive collections and Eclipse collections now for list, set, stack, bag, and map, and all combinations of primitives. So all 8 primitives are supported. And I guess we can fast forward now to what we're going to talk about today.
Yeah, and today's problem is a bit different, right? So that was, I don't know, Dark Ages? Can I say that? No, I don't know. But, I mean, it was back then. It was 15, 20 years ago. Actually, 20 years. Okay, well, anyway. But now things are different. Now we have super powerful machines. Our laptops are pretty much as powerful as servers back then. Our watches and phones have more memory and all this than computers back then, right? So you'd think it's not a problem. We have cloud, we have all these kind of things. But now we do play around quite a bit with data. So you want to process data. Nowadays we import a lot of data. We do a lot of data science and statistics, machine learnings, all these kind of things. And we wanted to look at this from the Java perspective, and it's like, wait, why are we using all the other languages? Why can't we use just Java for this? And how can we do it in an efficient way? And how can we actually measure the memory efficiency of the whole thing, of the data structures that we're creating? If you've been programming in C and stuff like that, you probably are more forced to think about memory you allocate and all that. In Java, you're just like, you just create stuff. Garbage collector will come and take it if you have to, and everything is just peachy. But it's not, right? It's when you get into big, large data sets, it's not. And the other thing we really wanted to have a look at is how do you handle this thing of rows versus columns? Rows is that way, columns is that way, and this object-oriented way of thinking about things, it's kind of thinking in a row, because you have a row, you have an instance of something with a bunch of parameters, kind of like a row in a table. But you have also column-based approach, and we wanted to have a look at this and which one is better. So what we tried to do is to try to compare, and we've just been comparing and looking at that. There are some other libraries that we kind of mention here and there also in references. But here we ended up with Java collections, so whatever battery is included comes with Java. We also looked into how Eclipse collection behaves and what it does with different data structures there as well. And we also looked into something called data frame EC. So in case you wonder, EC actually stands for Eclipse collection. So there was another person, Vlad, he actually built this data framework on top of using Eclipse collections in a background as well, but we'll talk a bit more about that in a second. Let's talk about the data that we've been using, that we've been playing around with. So I wrote a Java code, piece of code. I can't say script because, for reasons. But a piece of Java code that would generate automatically random data sets of a specific parameterized number of lines, and data looked like this because we travel to different conferences, speak at different conferences. Then we just picked just a list of conferences one of us or both of us have been speaking at, and so this is the data set. You have an event name, we have a country, city, started, in date, basically a string of a date. What kind of sessions that conference has, number of tracks, number of sessions, number of speakers. That's just kind of data to have some numbers and stuff. That's why they're exactly the same. So this is pretty much pre-printed CSV. We're using ASCII doc to generate all this. So they had just a function you paste in CSV and just creates table for you. So that was nice. And so we generated quite a lot of data. We went kind of a little bit overboard on that, and we did like 1 million rows, 25 million rows, 10 million rows. So, and you can see that the sizes of just the files are down there. So 1 million, a little bit shy of 90 megs, 10 million, 10 times, so almost 900, and 25 million was, well, 2.2 gigs on a disk. We generated also random event names, so basically names were just gibberish random. Fixed set of countries and city names just within a set that you just pick and put there. And the dates were limited to any date in 2023, just because. All right? How did we measure stuff?
Okay, so as we were like starting to figure this out, and way back in the day, in the dark ages, as Rustam said, the tools we had available were somewhat primitive. Used to use JMap histo, and if you've ever used that and outputted basically your heap, with the top objects occupying your heap at the top, you can't really tell like where your arrays or strings or anything are coming from. And there's a great tool, and I think if nothing else you come out of this talk, you should be aware of this tool, and this is something you can use in your own code to start to understand your own objects and how they're laying out in memory, and actually the cost of the thing. So luckily we have in the audience the creator of the tool, so thank you for joining us today, Alexei. There's an article here I referenced called Memory Layout Objects in Java. It's on Baildung. There's also a question on Stack Overflow. So when we first started using the tool Java Object Layout, which is an OpenJDK tool, we were using Java 20, and we actually were using records, and I couldn't get it to work initially, and I actually pinged Alexei and actually asked this question on Stack Overflow and found out like there's this VM flag you actually have to set to get records to be able to work with records, but it works fine. So there's a question and answer out there on Stack Overflow. Just set magic field offset to true, and you're good to go. So it's a great tool. Once again, you should definitely take a look at it. You're going to be seeing the output from JAL in a bunch of the slides going forward. So.
Yeah, and memory considerations. When we talk about memory considerations, what do we actually mean by that? Well, we're going to be looking at boxed and primitives. So whatever primitive values you have in Java, there are also boxed versions of that. How does that influence memory? We'll have a look at that. We'll look also into mutable and immutable data structures. So same data structure, same everything, just one of them is mutable, one of them is not. We'll look into something called pooling data. In case if you know what it is, cool. If you don't, just bear with us for a second. We'll get back to that. Row-based versus column-based. I mentioned that a little bit already. So this is what we also will be looking at. Again, object-oriented versus table or column-oriented structures, and we'll also look in what the future will bring. Looking into the big crystal ball of the Duke himself.
Okay, so we're going to start really simple here, and there are two classes up on the screen here if you look. And first question I'd ask you, looking at these two questions, like what is the difference between these two classes? Anyone want to blurt it out?
Just shout. Just a little bit louder, I can't hear it. Yes,
that's
exactly
correct. So on the left you've got box types, on the right you've got primitive types. So you're looking at these two classes. Effectively they're going to contain the same data, and now what we're going to do is actually take a look at what does the memory footprint look for.
The first output of JAL.
So this is the first example where we're using JAL to actually output the memory layout and footprint. So we use a class called graph layout. We call parse instance. We create either the boxed version or the primitive version of the class. Just call to footprint, and I'm just using system out println here. So this is the actual code, and this is the actual output for both of these classes. And what you'll see for the boxed version, right? Obviously, you've got a lot more objects that are being created here. So in total, we're creating 17 objects, right? So we've got all 8 of those values, which are going to be represented with boxed wrappers. Each one gets kind of 2, so 2 booleans, 2 bytes. And you can see the average cost of each object and the total cost. Looking down at the bottom, you can see for that class, total cost is 368 bytes, right? Now, if you look at the primitive version, so only one object gets created. It's the class, it's the instance of the class itself, and it's only a total of 72 bytes, right? So it's significant savings. It's over, I guess over 5 times difference, right, in terms of the cost. And what's interesting is think about that. It's 5 times the cost for basically, in most cases, just having an uppercase letter in the name, right? Now, this is the kind of stuff that if you rely on boxing and auto-boxing in your code, you can have hidden bloat, roaming around in your heap. Now, if you're not creating millions of these things, maybe it's not hurting you, but it's something I think to be aware of, actually, what's happening. So if at all possible, don't box primitive values, right? Keep them as primitives. Now, that can be hard if you don't have a primitive collections framework and you use maps or whatever, but something to be conscious of. So we're going to look at this. So in this example code, what we're going to do is we're going to create 3 different sets. So we're going to use a JDK hash set. We're going to create a set of integers from 1 to 10, right? Just interval class actually just holds on to, effectively, it's a list from 1 to 10. We'll construct the hash set out of that. We're going to use an Eclipse collection set just to have a comparison of an alternative set implementation. And then we're actually going to create a primitive set from 1 to 10. So it's exactly the same data, all contained in sets. We're going to use JAL to output each of the instances and look at the footprint. So the question is going to be, what is the difference going to be between these classes? So I won't keep you in suspense. We'll go look at it. Ta-da. So what's interesting is if you look at the output for Java util hash set, what you see immediately, and for I'm sure many of you already know this, Java util hash set's actually backed by a Java util hash map. So what you immediately see is that you have a hash map instance in there costing 48 bytes. You then have an array, and at the top you see that square bracket L, Java util hash map $node. That's an array of hash map nodes. You also have 10 actually hash map node instances. So hash map $node, for those that don't know, that's actually the implementation of map.entry inside of hash map. So you've got the 10 integer objects, so we're actually boxing the int values, so we get 160 bytes to box the integer values. So in total, to hold on to 10 ints in a set, in Java util hash set, it's 640 bytes, right? We take a look at the Eclipse collection set, and the set implementation is different. It's not backed by a hash map, as you can see. It does have an array of object that's costing 80 bytes. It still has the boxed integers. It's still an object collection type. But in total, it's 272. So it's half the cost of the set. So look at the primitive set from Eclipse collections. What you'll see is all the boxed integers are gone now, so we're saving that 160 bytes, right? We just have the cost of an int array. And then the object itself, so 120 bytes, right? So cutting the cost in more than half again. So recommendation, if you're using Java util hash set, just be aware it's a porky object, right? It's a bit bloated. So just be aware if you're using these things, especially if there's either a lot of them or very large, it's going to cost you a lot. Obviously, once again, don't box primitive values if you don't have to. That's costing you as well. Okay, next example, and this is a comparison of a mutable type and an immutable type, right? And these are types that are both in the JDK. So we're going to use Java util hash set again. We're only going to store 2 ints in the hash set this time, right? So we've got the numbers 1 and 2 in it. We're going to create a set, so using set copy of. This is actually going to create an immutable set. And if you look down at the bottom on line 15 in the code there, you'll see it's actually going to create an instance of immutable collections $set12. The first time I read that as set 12. That's not what it is. It's set12. It holds on to either 1 or 2 instances. But you look at the difference. To hold on to 2 integer values, right? It's either with hash set 272 bytes, or so that's the mutable option. And if we look at the immutable option for its set copy of, it's 56 bytes, right? So once again, 5 times the cost. Recommendation here is, once again, if you can, avoid using Java util hash set. But if you're going to load data into memory and keep it around for a while, it can be more optimal to actually take your mutable structures and turn them into mutable structures if you know the data is not going to change. So you effectively get this like trimming and compression factor going on.
How many of you knew that there is different implementation, like set 1, 2, and the other sets? Anyone? Okay, there are a few hands. That's good. For the rest of you, you will see why in a second. There will be some graphs and stuff.
Yeah. So
there you go.
Yeah, first graph. So first thing, I guess, this graph is actually from a blog I wrote called "Sweating the Small Stuff in Java," and this is actually comparing two immutable list implementations, both in the JDK and in Eclipse collections. And definitely, if you're interested in finding out more about stuff that I did 20 years ago, it'll explain why we arrived at this. But effectively, like for the immutable list implementation, in the JDK, it's optimized up to size 1, 2. So you wind up with a mutable, let's say, list $1, 2. And for Eclipse collections, we actually optimized it up to size 10. And what you'll see is, like, if you've got a problem, this is the problem I had 20 years ago. I had tons and tons of very small lists. And typically, at the time we did it 20 years ago, we optimized to size 6. When we implemented immutable lists inside of Eclipse collections, we went up to 10. As it turns out, we can actually go up to 11. And it would be the same cost as 10. If you look, you can see this plateau where like every 2 costs you. And that's really, you're able to jam 2 references in the object alignment space, right? So you get 8 bytes for object alignment, stick 2 references in there. So we could fit another reference into size 11. And what you can see is you get a reasonable savings all the way up there. And what are you saving? You're saving the cost of the backing array. Now, the nice thing, with these, instances, different types at different levels as well, like you actually get a named class, and you'll actually get to see some examples later where the named class, when you're looking at like in a tool like either JMap or even JAL, having the named classes that have the size and the name, it actually tells you more about the data that actually is in your heap, and you'll get to see that in a bit. So just beware up here. Saving memory is one thing. So back in the day, we were more concerned about memory. There is a downside, though, of having lots of implementations of the same interface. You can wind up with basically a situation where you have megamorphic calls, where effectively a call will wind up with like in a virtual table lookup. So that's actually why in the JDK, they only have 2 implementations of the immutable list. They support 1, 2. They support, up to size n, which will have the backing array, but they want to keep it at 2 so that it's optimized really combination of memory and performance. But you lose memory after size 2, but you don't lose performance, right? So if performance is your concern, then might be better with the JDK. If memory is your concern, then it might be better with Eclipse collections.
It's also about your data as well. And so now we talked a little bit about different things, and when kind of name drop Eclipse collections and data frame and stuff like that. What is actually that? So a quick kind of overview, bird eye view of the whole thing, and we kind of like those building bricks thing.
Does everybody use Legos?
Anybody? Yes. Good.
Yeah, love Legos.
So we have actually from courtesy of our friends downstairs from Missoula, we got a few of those. We have, I think, 3 or few out there. So if you ask good questions, something, I don't know, we'll do the contest later. You can get those, and we have a little helper here. And we kind of we were thinking, how should we try to explain these things and try to relate to those different levels or different ways of doing that. And then we were having we were talking on and then we looked at the Lego boxes that we had lying around, and then we realized, hey, we can do this in Lego world. So Java Streams is a kind of like a regular Lego that you see an example of up there on top. It's and the fun thing that all of those boxes, they have age limits, and it's the cool thing is like it's kind of, it tells you about the complexity and stuff, but it's the same here. So Java Streams is basic building blocks. So it's 9+ years. Of experience? No, I'm not going there. Basic building blocks. Some assembly is required. You'll be given pieces, and you still need to put that thing together. I did a speed run of this just before our talk because I got this.
Took him 3 hours.
Yeah, no, don't
Just
tell
joking.
it. Don't tell anyone. Well, I did the speed run out there because I had a very bright idea of having this guy with us. It's more of a low-level control. You actually can build things, but you need to do the fiddly things. And it's also a row-based domain objects, basically, right? It's domain-oriented programming kind of stuff. Eclipse collections is a little bit more like Lego Technic. You can use the same basic bricks, but it also has some extra things. You have like this little bent, fancy things, and you have a fancier wheels and some special stuff that actually fits to the original ones, but it has some specialized stuff. So goes with for Eclipse collections as well. So 16 plus is the age limit apparently on this box, that particular one anyway. And but it's performance optimized, so it's optimized for a specific task for making things looking like a car. But it's still compatible with the building blocks, like I said, and it's still row-based, so it's a domain-oriented kind of stuff. So when it comes to data frame EC, it's a kind of a bit more interesting thing, because it's more like Lego Mindstorms. I don't know if Lego Mindstorms, anyone? Good. So those things usually come with, again, the same basic bricks, some extra Technic stuff, but they also have some fancy controllers and stuff that you can program. And so you can do it here as well. You can actually think of Eclipse collections. If you haven't worked with those kind of things, think of it as a little bit of a smart Excel spreadsheet. You can actually do some smartness in those, and you can actually, add some logics and ways of generating values from other things and doing stuff. It's even more specialized building blocks. It's high-level approach. You don't have to think about all the small fiddly things. It's still compatible with the basic building blocks, like I said. It can be programmed to accomplish tasks, and it simplifies some of the tasks because you don't have to do the fiddly stuff. And it has a column-based approach now. So you don't really need to think about objects in an object-oriented world, but you need to think about tables and stuff. So, Conference Explorer. So we actually created like a class which would contain all the conferences that we've been reading through our ginormous CSV files. To do that, to do the object-oriented version of that, or a row-based approach, we had to create a record, or, technically class, but, now we have records, so we just went with records. And it contains some attributes for the conference, the things you've seen, event name, country, and so on, so on, so on. When you want to put it into a Java stream, well, you will just, at least one way of doing that would put that thing into a set, and then you just smack the whole object of the conference record into it, and you say, well, we have a set of conference objects or records. Eclipse collections, pretty much the same, it's just a different kind of object, so now it's not a set, but immutable set. At least one way of doing that again. There are different other data structures you could put that thing as well. And for data frame, we had to do it differently. So that was actually a data frame object. Again, think of it like a spreadsheet object, which contained all the conferences with all the information. All the things that you see in the record would be there already. And we also needed another table, spreadsheet, whatever, for country codes, because we wanted to generate some flags and emojis and stuff and things out of it. If you are interested, so now we're focusing a lot on the memory part of this, but if you're interested in understanding how APIs work and how you program those and how you actually do that, we've done a talk at DevNexus this year and also DevOps Greece a little bit earlier this year, where we actually went through the APIs of those three different approaches. So it's a little bit different talk, more focused on that. You can watch that one online, and there is also slides that are available. By the way, all the slides that are here, they are on GitHub, and you will see the link at the end. So just in case you want to have some of those and have a look at the code. And code is actually, the cool thing is that all those links here are actually the real links into the code base. So you can just click on it, and it will just jump into the code. Right. Conference Explorer. memory cost comparison. So we tried to create a little bit of a generate a little graph, or we did generate a graph that would group them by implementation and also a way of a type of data structure. So you would have a Java set, Java list, Eclipse collection set, Eclipse collection list, and data frame EC, because we don't have sets and lists and stuff. It's just one table. And you can see here also the most fun thing you can probably see here is the difference between mutable and immutable types, especially for sets in Java. You nearly go half the size of the memory. And here we also see that, well, immutable lists are maybe a little bit more costly than sets, but not that much. And Eclipse collection sets are pretty much the same, and so on and so on. But there is also the thing you see there, and that was kind of puzzling us a little bit, why data frame EC was half the size, because all the green ones are roughly the same thing, right? All the immutable ones. But data frame was just half the size, and we were just scratching our heads, and we were like, this must be a bug. There's something wrong there, and something is like, this is weird. After a little bit of head scratching and stuff, we realized there was this magic thing called pooling. How many of you have heard of pooling? 1, 2, 3, 4. Okay, 4 or 5 hands. Not that many.
How many folks have, I guess, heard of the intern method on string? Okay, so
cool.
We're going to talk a little bit about that later. So
nice. So what we realized is that data frame EC had built-in pooling. You know, hence what I said. You have a lot of high-level approach. All the Figly things are done for you. It wasn't for all the other ones. And then we realized, oh, let's try to do that. And then we actually went ahead and implemented that. And we kind of did cheat a little bit for Java, I guess I would say, right? Because the pooling implementation
we use the same pooling implementation for both. So
we use the same pooling implementation from Eclipse collections just to prove the point that that's how it is. And here you see also the difference. Without pooling, that's the thing that you saw on the previous slide here, the green ones. And the green ones here are with pooling. And now we're getting to the level of Eclipse data frame Eclipse collections, easy. So it's not about the data structure, not necessarily, but it's also about your how your data looks like and what you do with your data. So pooling, for example, significantly reduces duplicated data data cost, but that has also mean that your data has quite a bit of duplication. So we have 1 million rows. All the date pairs, they're from 1 year. So it's like 365 possible dates that you have, right? Or 60, whatever that year.
Yeah. Just go ahead to the next slide and we'll answer a lot of the questions in terms of the data.
There you go. Okay.
So I guess first thing we talk about, since it looked like a lot of folks aren't familiar with the idea of data pooling, and obviously I think more folks are probably used to the idea of like thread pooling or database connection pooling. But the way I think about a pool is a set of unique values that you can put things into and you can get them out. And what you want is uniquing to happen, where if I put something into a set, I want to be able to get that value back out. As it turns out, as we know in the JDK, or maybe don't know, there is no get method on a set. So when you put stuff in, you can check if something's in there, but you can't get that unique instance back out that the set's holding onto without iterating or using a stream or something. There is a Stack Overflow question, which I've answered. I got the accepted answer, called get an item from a Java set. It turns out in Eclipse collections, our set implementation, we have a separate interface called pool. And pool has both get and put methods on it. And our set implementation implements both set, which doesn't have a get method, but also implements pool. So our unified set is basically both a set and a pool, and you can use it in either way. So we actually used the class called unified set for doing it. And it turns out data frame EC was doing exactly the same thing. So the pooling that it's doing, because it's built on top of Eclipse collections, the guy Vlad who built the library knew about unified set, knew it was a pool, so he just used it for the pooling that he did for data frame EC. So what is a pool useful for? It's useful for uniquing, for reducing down the duplicate values of a specific value in dataset and memory. So we talked briefly about string intern. So there is pooling that happens to the JDK. String intern is a good example, right? So all intrinsic strings, when you create them, or I'm sorry, literal strings, not intrinsic, sorry. Literal strings that you write get interned by the compiler itself. You can call the method, it's a native method, and it will, put it in this pool that you can't see, you can't actually access the pool, see it in. It's, I think it's on, as of Java 7, it was added to the Java heap. Before that, I think, I forget exactly where exactly it was, I don't know if anybody knows, but it was moved to the Java heap. You can use that method for pooling. There are other pools that happen as well in Java, sometimes referred to as a cache, sometimes a pool, but if you look at all the boxed integral values like short, byte, long, and integer, they all cache the values from -1, I think it's from -128 to +127. So they're just keeping an array. And this is so for that range where you may get some common values, especially for 0. There will be a lot of zeros maybe. You can guarantee then if you're using the value of method, you're going to get one instance of 0 in memory. So mentioned data frame EC uses unified set. The most important thing, and I think you can see now the breakup of our data, most important thing to understand is how your data is structured and what you're actually loading into memory. So as it turns out, when we were loading all the cities, as we went from, let's say, 10 conferences to 1 million. Now, obviously, it's nonsensical. How could we ever have 1 million conferences? It wasn't the point. We just wanted to generate that volume and see what happened. But because we only had 6 unique cities, right, uniquing was quite helpful here, right? Instead of having 1 million strings for city, let's have 6, right? So pooling helps significantly for city. For start date and end date, as Rustam was saying, like, we were only covering data for a year, so we only have 364 dates. So I don't need to have 2 million dates for start date, end date. I just need, 364 for each.
And actually, if you think like, oh, that's kind of cheating, well, it's not, because, like, for example, think for dates, right? I mean, how many cities are there in a world? I mean, it's still not 1 million that have different conferences, at least not the ones that would travel to or something, right? So realistically, it will be lower. Dates even more, because like 365 days a year, okay, fine, we've just used 1 year. Let's say we've used 10 years or 100 years. It's still like for 100 years, there will be 36,000 different dates.
Yeah, and the key thing there is just, once again, understand your data and what you're loading in, and you can find ways then of optimizing. So real quick on the bottom part with the session types. So when Rustam was showing like the CSV data we're loading in, there was one column that actually had 3 potential values in it. And you go think about a conference you go to, it may have workshops, lightning talks, regular conference sessions, right? And it could have a combination of those. And those are represented in either a set or a list. And this is actually showing when we're outputting using JAL, when we're using Eclipse collections, immutable types, we actually see the size in the name. So you can see we have singleton set, doubleton set, tripleton set. I think sets go up to 6. And you can see then the number of instances of those combinations. Now, it's interesting because you can say, well, if you've only got 3 things, you can actually really, really highly optimize that. Just use a very small number to represent, let's say, a combination of 3 different things, right? You don't even need to use a set. So there are things like that you can do if you want. And I think, yeah, so real quick, this was just the pool implementation we used for the row-based solution. So we created pools for strings, for dates. I created pools for lists and sets. And you can see I'm just instantiating unified set. But the interface that I'm using there is the pool interface. And when I want to use the pool, I just say, if pooling is enabled, I do string, let's say string pool put. Put will actually either return the value you're putting in if nothing's in there, or will return the value that's already in there. So that's where the unique will happen. Okay. This is what I had to do. And this is where once you start using pooling, it gets a bit obtrusive in your own code, right? What I had to do is actually create a special constructor for our conference record and make sure that when I'm instantiating the conference record, we pool. And it's interesting, there is pooling. I don't think of it as pooling usually, but we have an enum called country. And you think about it, like an enum is really like a pool of particular values. They're just all hand-coded, but we pull the strings, and this is what the code looks like. So it's more obtrusive. We didn't have to do any of this with data frame. Okay. Real quick on, I guess, looking at the benefits, challenges of different things. So with row-based structures, you can do custom tuning. Right? If you really understand your data, you can figure out, let's say, data ranges. You can change the types of things. You can use things like pooling. But you do have these like consistent challenges. If you're going to go row-based, you have to create objects, and they have object header costs. And we're going to talk later about, there's attempts to, let's say, reduce the 16-byte cost down to 8 bytes with Project Lilliput, right? You get the object alignment cost, right? So there are things you have to, be aware of challenge. With column-based, you lose the object header cost because you don't have rows. You wind up with like, a single column of the, or object, which effectively is going to be some collection with an array. And pretty much, especially if you've got primitive types, let's say, any of the integral values or even like doubles or floats, there is no, object header cost for each of the values in there, right? So you also get this like great compression, cache locality, performance can be great, especially if you're dealing with primitive types, right? But your tuning is limited to the types you support. And one thing we found with DataFrame EC, and it's open source, we could always go add it if we wanted to, the only integral type it supported was long, right? Which is going to cost us 8 bytes for every long value. I can't use things like int or short or byte, right? And that is actually going to come in here. So what we wanted to do is we wanted to see, like, can we squeeze more memory out of the row-based solution? And we were able to. And you can see, like, and I only optimized the column for Eclipse collections list. I could have done this for all the row-based solutions, but we were able to squeeze like an extra 10% of memory benefit over, let's say, comparing the row-based to the column-based. And the tricks that we were doing here was, well, we've got these integral types, and we started off with just 4 ints for like track count and session count, and I think it was cost and stuff. But like we were able to take the int values and say, well, track count, how many tracks can you possibly have at a conference, right? You're not going to need like 2 billion, right? So we can shrink that down to byte. Maybe 128 is just fine, right? Or 127. And then we look at the session count one that way. Hey, we don't need an int for that. We can use a short. And what we can do is actually reduce, let's say, 16 bytes down to 7 bytes by changing the primitive type that's used for those ranges. We then did this trick, and this is kind of like Rustam was getting into. It's like, well, if we look at the dates, we don't actually need to have a reference to both start and end date. We can actually create a pair of the dates, and we have a limited combination of pairs. And it turns out there's 66,000 possible combinations plus of start and end date for within a year or so, and that's less than 1 million. So we can actually get rid of an object reference, and that'll save us another 4 bytes. And in the end, what we were able to do is, for the row cost, we were able to get the cost down from 56 bytes to 40 bytes. And you can say, well, who cares about 16 bytes? Well, you care about 16 bytes if the multiplier is huge, right? And so that's the interesting thing. You do start to care about that once again when you've got a large number of objects. And that's when you go to 25 million rows, all of a sudden, like that 10% starts to look interesting, right? So you can see, like, by doing that manual tuning, we're able to, let's say, get from 2.8 gig down to 2.5 gig, right? And all of a sudden, too, like I showed the number here for the size of the CSV file. And it's kind of, I don't know, I found it kind of interesting that the memory is getting closer to the size of the file. And for some reason, that makes me feel better. I feel awful if like the memory is like, much larger than the file itself. It's like, what am I doing wrong? The memory's taking so much. But so one interesting thing we found as we turned the volume up to 11, if you will, going from 1 million to 25 million, the code that was running blew up, and we were using Jackson CSV for reading in the CSV file, and we were just doing something dumb. We were using mapping iterator read all, and what that does is it reads in a list of maps all at once for all the data, and then we were going to convert that to the conference records. It just couldn't load all of that, so I was like, use it as an iterator and iterate one run record at a time, and it's fine, right? And that's the kind of thing you discover when you turn the volume to 11, and all of a sudden, like, you gotta have a different strategy. You can't just load everything at once and then copy it over to something else, right? So, and that's what we had to do there. So,
and I mean, again, if you think about this, like tiny little bit changes in the memory and all that. Think about that in, like, you would say, well, so what? But you think about that in a world of cloud and everything where you're actually paying per whatever gigabyte of memory you're using or per kind of a size of a machine that you want. By doing that kind of smaller things, it will actually, I mean, you will need a smaller machine. You will need less resources. And if you don't really care about, like, money is not a problem, you can think about environment. You have less resources consumed, less used, the green stuff. That's also a good way of thinking that. So I'm kind of trying to motivate you to think about that, whatever you care about, like one green thing, the other green. But anyway, so the future of Java. What will come in the future? What we'll be seeing in the near future? So one of them is Project Lilliput that we have mentioned a few times already, but it's so this is something is going to happen with the object headers. So they're working on trying to reduce that from 128 to 64 bits, and excuse me, and that will do something with the data. So maybe the same metrics that we've been running and getting will not be like that with that project already in live.
That Project Lilliput's just going to help everything. Forget about like what you're using. Like
exactly.
Every instance of an object is going to benefit, and you're going to see an overall savings in your heap. Is the hope so?
Yeah, and then we have other things. We have things like Project Valhalla, which is many things, but in this case, it's especially this value object things that we would like to kind of bring to attention, and it's also will do something with reducing the footprint of your applications as well. So another thing that is a tiny little bit different, but still in the same ballpark, is Project Amber, and that is more about. So first two were more about reducing your footprint of memory and stuff, and this one is a bit more about the way you think about things. So more of data-oriented programming instead of object-oriented, or, well, complementing it. Yeah, and the links to all of those are in the slides, and that is the link to the slides. So the QR code there will bring you to
get your camera out and.
Yeah, well, I mean, if you don't want to follow QR codes, there are the clear text link is at the bottom there as well. It's the same repository there. And there you'll also find the repository. So if you remove the perf at the end, you'll find the repository to the previous talk that we mentioned as well.
Yeah, and both the slides we're just using ASCII doc for presenting. So in the slides and the code are in the same repo. Yeah. So.
And, well, let's just sum up. So we have just a few more minutes left. The idea was to try and see what we can do with all this. And we could see that, well, it's feasible, flexible, and fun to do this thing of data-oriented programming. Understanding and measuring things was really fun, and trying to actually measure and see what tools we can use for that, how we can reduce it with some techniques like pooling. Object compression was an interesting thing that we got to play with. We also did play with column-based, right, tabular data, and we learned how primitives can generate more memory savings, all those kind of things, and smaller integral types as well. And domain-oriented row-based, so domain-oriented or row-based data structures are also more flexible, and they can be more fine-tuned, but you need to do some work as well.
And we just did start taking a look at so there are multiple data frame solutions that are available for Java. Right. So data frame EC is what we looked at and focused on for the talk. In the code, I believe we do have included a dependency on JTableSaw, so it's another data frame library for Java. I think Kotlin has its own data frame library as well. So if you haven't looked at data frames, there are alternatives out there for column-based, more table-like data-oriented programming. So.
And there is a bunch of appendices that you can have a look at, all the things that didn't make to the main slides because of time and space constraints. But, there is a lot of fun things you can have a look at as well there. And
we've got 2 minutes left. So.
We have 2 minutes left. Questions? We have some dukes to give away.
Oh.
One there, and I heard someone. Yeah, there was one there. Okay, you go first. Repeat the question.
So I guess, does the compiler solve the problem, I guess, inlining, for boxing and unboxing, right, with primitives? That's a good question. I think it would be great if it did. I I haven't seen it happen yet. Whether that's going to happen or not, I don't know. I don't know if there's someone who knows better than I do.
But that is Valhalla. This is inline types.
Yeah.
We're all waiting for Valhalla.
For inline types. That's what Alex has said. All right.
Next question.
Yes, over there.
Have you looked at library implementations on other languages like Tabular and DataFrame for inspiration on?
Yeah, if we've looked at other implementations.
What was the other library?
DataFrame, for example, or Tabular.
Yeah, so implementations in other languages.
Yeah, we did. Oh, in other languages. No, we haven't looked in other languages. I'm aware of, once again, the Kotlin data frame. We looked at JTable saw.
Yeah.
It's really down to like how many things we can spend time on and comparing what we can fit in 45, 50 minutes. So
I've been looking a little bit into what's it called? Brain freeze. In Python, so I was looking into pandas as well, just to get a little bit of inspiration and things, because I actually was like missing some things in Eclipse data frame EC, and I would just like write that and contribute back to the repository. And some of the things that I would kind of look a little bit into the pandas and how they did things, and just try to get inspired by that.
Yeah.
But not more than just APIs and calls, not the actual implementation, because that was different.
Yeah.
Yes.
I was curious. Suppose you have one column with a small value between 0 and, let's say, 255, and you use the column-based approach, and you convert that to something like a byte array instead
Yeah.
of something with object references or the object pooling. You would also get like quite a huge benefit, right?
Yeah, that's that. So the question is, I guess, if you have a column like, I guess, a byte value like, you know, up to 255, let's say the size. That, yeah, if you're using a column-based approach, you will get a benefit, and that's actually one of the promises with a library like DataFrame, because you get the values are going to be stacked together in a single primitive array. It's going to, you know, if depending, the whole array may fit into memory. You can get, let's say, the cache, you know, benefits moving from, let's say, level 2, level 1, you know, from main memory. You don't have to, let's say, dereference, you know, stuff and like you would with object references. So you can get a significant benefit if you've got, let's say, primitive data, and it could be for any of the types, not just the.
But also think
ranges.
about this, like when you work with data, sometimes you can specialize and optimize it, super optimize it, but also sometimes you just work with CSV files and you just like, it's kind of use it once and throw it away kind of thing, and you don't want to do all this kind of stuff and map all that manually, right? So sometimes, the short version is the kind of the best consultant answer you can give is like, it depends, right? But it actually does. Depends on your data, and depends on what you're doing, and depends on your application, a lot of things.
Well, I see we're time's up, so yeah. I think the three folks. Oh.
One more question.
One more question.
Is there any? Does this kind of work actually give any impetus to providing us with unsigned primitive types like int, byte, and so on?
Does this give us any impetus for unsigned types? Like, no, it's not something I think, you know, I've even, you know, been considering looking at. I think that's really other folks may be having the impetus for that, but yeah, not I would say myself for this talk. I don't know about yourself.
No.
It does actually, with unsigned data types, you can have more opportunity to compress, as you did.
Yeah, I think, once again, I don't know if there's any work that's happening, let's say, in the JDK on that type of front. I know that this has come up for many years, people asking why don't we have unsigned types and stuff, so, yeah.
All right, we'll say thank you very much. You'll find us on social media with those handles, and if you have more questions, we're more than welcome to come down and talk to us.
And I guess the first three folks that asked questions, if you want to take one of the Dukes, feel free, and if anybody wants an Eclipse Collection sticker, feel free.
Thank you.